Hi friends, welcome to my channel Magic Sir of Mathematics with Magic Methods. I will help you to improve your knowledge of trigonometry. The purpose of making this video is to develop the student skills in solving trigonometric examples. Today we will verify a trigonometric identity with the help of PowerPoint animation. Occasionally, we will use Pythagorean identities and algebraic formulas as needed. Friends, before solving this example, we will discuss the importance of conjugate multiplication. Look at the algebraic and trigonometric fractions given below. We will use conjugate multiplication to balance these type of fractions. First, when we deal with real numbers, the conjugate of a plus b is a minus b. Just change the sign between two numbers in a binomial. The sum of binomial is equal to a plus b plus a minus b. Here, negative b cancels with positive b. Therefore, the sum is equal to twice a. The product of binomials is equal to a plus b into second bracket a minus b. Use the difference of square formula. We get the product equal to a square minus b square. Let us consider the above table. Here, a plus b and a minus b are the conjugate of each other. Their sum is the rational number twice a, and their product is the rational number a square minus b square. Friends, when both a and b are rational numbers, it is useless to say that the conjugate of a plus b is a minus b. Second, when we deal with surds, here 1 upon a plus root b is an irrational number, so the conjugates are used to rationalize the denominator of a fraction. The conjugate of a plus root b is a minus root b. Just change the sign of irrational part. The sum of binomial is equal to a plus root b plus a minus root b. Here, positive root b cancels with negative root b. Therefore, the sum is equal to twice a. The product of binomials is equal to a plus root b into second bracket a minus root b is equal to a whole square minus root b whole square. A whole square equal to a square and root b whole square equal to b. Therefore, the product is equal to a square minus b. Let us consider the above table. Here, a plus root b and a minus root b are the conjugate of each other. Their sum is the rational number twice a, and their product is the rational number a square minus b. You will learn the concept of complex numbers at the higher secondary level. Today, we are going to discuss complex numbers just for your knowledge. Look at the third point. When we deal with complex numbers, here 1 upon a plus ib is a complex number, so the conjugates are used to rationalize the denominator of the fraction. Here a is a real part and b is an imaginary part. I is known as iota and I square equal to minus 1. The conjugate of a plus ib is a minus ib. Just change the sign of the imaginary part. The sum of binomials is equal to a plus ib plus a minus ib. Here, positive ib cancels with negative ib. Therefore, the sum is equal to twice a. The product of the binomials is equal to a plus ib into second bracket a minus ib is equal to a whole square minus ib whole square is equal to a square minus I square into b square, where I square equal to minus 1. Therefore, the product is equal to a square minus minus 1 into b square is equal to a square plus b square. Here, a square plus b square is the rational number. Let us consider the above table. Here, a plus ib and a minus ib are the conjugate of each other. Their sum is the rational number twice a, and their product is the rational number a square plus b square. Friends, now you are well prepared to obtain the conjugate of binomials. We are going to discuss the use of conjugate in trigonometry. It will help us to balance trigonometric fractions. It is one kind of adjustment to verify trigonometric identities. Look at the fraction 1 upon sec theta plus tan theta. The conjugate of sec theta plus tan theta is sec theta minus tan theta. Just change the sign between sec theta and tan theta. The sum of binomials is equal to sec theta plus tan theta plus sec theta minus tan theta. Here, negative tan theta cancels with positive tan theta. Therefore, the sum is equal to twice sec theta. The product of binomials is equal to sec theta plus tan theta into second bracket sec theta minus tan theta. Using the difference of square formula, we get the product is equal to sec square theta minus tan square theta. And we know that sec square theta minus tan square theta equal to 1. Let us consider the above table. Here, sec theta plus tan theta and sec theta minus tan theta are conjugates of each other. Their sum is equal to twice sec theta. And the product of binomials is equal to 1. Again, look at the fraction 1 upon cosec theta plus cot theta. The conjugate of cosec theta plus cot theta is cosec theta minus cot theta. Just change the sign between cosec theta and cot theta. The sum of binomials is equal to cosec theta plus cosec theta minus cot theta. Here, positive cot theta cancels with negative cot theta. Therefore, the sum is equal to twice cosec theta. The product of binomials is equal to cosec theta plus cot theta into second bracket cosec theta minus cot theta. Using the difference of square formula, we get the product is equal to cosec square theta minus cot square theta. And we know that cosec square theta minus cot square theta is equal to 1. Let us consider the above table. Here cosec theta plus cot theta and cosec theta minus cot theta are conjugates of each other. Their sum is equal to twice cosec theta. And the product of binomials is equal to 1. Now look at the fraction 1 upon sin theta plus cos theta. The conjugate of sin theta plus cos theta is sin theta minus cos theta. Their sum is equal to sin theta plus cos theta plus sin theta minus cos theta, where positive cos theta cancels with negative cos theta. Therefore, the sum is equal to twice sin theta. The product of sin theta plus cos theta and sin theta minus cos theta is equal to sin square theta minus cos square theta by difference of square formula. Friends, note that if A plus B belongs to R, then conjugate of A plus B is A minus B. If A plus B belongs to C, then conjugate of A plus B is A plus B itself. Let us check. Z is equal to A plus B, where Z belongs to C. Then Z is equal to A plus B plus 0 into I. Here, real part equal to A plus B and imaginary part is equal to 0. So the conjugate of Z is equal to A plus B minus 0 into I. Here, A plus B is the real part and the imaginary part is equal to 0. Therefore, the conjugate of Z is equal to A plus B, and A plus B is the complex number. Hence, we can say that if Z is equal to A plus B, Z belongs to C, then conjugate of Z equal to A plus B itself. Look at these two examples. The left hand side of these example is identical, not that their right hand side is different. Friends, now it is time to verify the trigonometric identities one by one. Look at the given example. We will discuss a similar example related to this example after verifying it. Let us take the left hand side of the equation. Let us first convert the left hand side in terms of sin theta and cos theta. We know that cot theta is equal to cos theta upon sin theta. Let us replace cot theta with cos theta upon sin theta. Again, replace cot theta with cos theta upon sin theta. Simplifying, we get left hand side is equal to sin theta minus cos theta upon sin theta divided by sin theta plus cos theta upon sin theta. Here sin theta cancels out, leaving us with left hand side equal to sin theta minus cos theta upon sin theta plus cos theta. For convenience, we may rewrite this step again. To balance the fraction, we may use the conjugate multiplication. We know that conjugate of sin theta minus cos theta equal to sin theta plus cos theta. Now multiply the numerator and the denominator with sin theta plus cos theta. Let us apply the formula of a minus b into second bracket a plus b is equal to a square minus b square. Let us suppose a equal to sin theta and b equal to cos theta. Here a minus b is equal to sin theta minus cos theta and a plus b equal to sin theta plus cos theta. Therefore, a square minus b square is equal to sin theta whole square minus cos theta whole square. That is, a square equal to sin square theta minus b square is equal to cos square theta. In the denominator, sin theta plus cos theta into second bracket sin theta plus cos theta is equal to sin theta plus cos theta whole square. Keep an eye on the right hand side and work as needed. We know that sin square theta equal to 1 minus cos square theta. Let us replace sin square theta with 1 minus cos square theta, and minus cos square theta remains as it is. In the denominator, let us apply the formula of a plus b whole square to expand sin theta plus cos theta whole square, that is a plus b whole square equal to a square plus b square plus twice ab. Let us suppose a equal to sin theta and b equal to cos theta. So, a square is equal to sin square theta and b square is equal to cos square theta, and twice ab is equal to twice sin theta into cos theta. Here 1 minus cos square theta minus cos square theta is equal to 1 minus twice cos square theta. Again apply the Pythagorean identity sin square theta plus cos square theta equal to 1. In the denominator, replace sin square theta plus cos square theta with 1. Here twice sin theta into cos theta remains as it is. So LHS is equal to 1 minus twice cos square theta divided by 1 plus twice sin theta into cos theta. Now compare the left hand side with the right hand side of the equation. It is clear that the left hand side is equal to the right hand side. Now enjoy the similar example with the same left hand side. Look at the next example. Let us take the left hand side of the equation. Let us first convert the left hand side in terms of sin theta and cos theta. We know that cot theta is equal to cos theta upon sin theta. Let us replace cot theta with cos theta upon sin theta. Again replace cot theta with cos theta upon sin theta. Now simplifying we get sin theta minus cos theta upon sin theta divided by sin theta plus cos theta upon sin theta. Here sin theta cancels out, leaving us with LHS is equal to sin theta minus cos theta upon sin theta plus cos theta. For convenience, we may rewrite this step again. To balance the fraction, we may use the conjugate multiplication. We know that conjugate of sin theta plus cos theta is sin theta minus cos theta. So multiply the numerator and the denominator with sin theta minus cos theta. In the numerator, product of sin theta minus cos theta into sin theta minus cos theta is equal to sin theta minus cos theta whole square. In the denominator, apply the formula of a plus b into a minus b equal to a square minus b square. Let us suppose a equal to sin theta and b equal to cos theta. Therefore, a plus b is equal to sin theta plus cos theta and a minus b is equal to sin theta minus cos theta. So, a square minus b square is equal to sin theta whole square minus cos theta whole square. That is, a square equal to sin square theta minus b square equal to cos square theta. Now apply the formula of a minus b whole square to expand sin theta minus cos theta whole square. That is, a minus b whole square is equal to a square minus twice ab plus b square, or is equal to a square plus b square minus twice ab. Let us suppose a equal to sin theta and b equal to cos theta. So a square is equal to sin square theta, b square equal to cos square theta, and twice ab equal to twice sin theta cos theta. We know that sin square theta is equal to 1 minus cos square theta. Keep an eye on the right hand side of the equation and work as needed. We may replace sin square theta with 1 minus cos square theta, and minus cos square theta remains as it is. In the numerator, again apply the Pythagorean identity. Sin square theta plus cos square theta is equal to 1. So we can replace sin square theta plus cos square theta with 1, and minus 2 sin theta cos theta remains as it is. In the denominator, 1 minus cos square theta minus cos square theta is equal to 1 minus twice cos square theta. So LHS is equal to 1 minus twice sin theta into cos theta divided by 1 minus twice cos square theta. Now compare the left hand side with the right hand side of the equation. It is clear that the left hand side is equal to the right hand side. Friends, let us consider this table. Look at these trigonometric factors and their conjugates. I have given some pairs of conjugates as a ready reckoner. These pairs are very useful in proving trigonometric identities. Please look carefully at their product and use the factor suitable for simplifying the fraction. I think it will help you to prove this type of example. If you have any further questions, leave them in a comment. Now watch the next section, that is screenshots at a glance.